Welcome to this first colloquium in the summer term 2024. As you may have seen on the announcements on Hephisto or per email sent by Richard around, we have again a cool and interesting full program of exciting talks covering many fields of astronomy and astrophysics. We have a number of local speakers like Andreas Sander and others. We have speakers coming as far as Australia. Alex Seeger will talk to us about how stars work and explode. And we cover from planetary scales to cosmological scales, the wide range. So in that sense, it is fitting to start with an astrophysical object that I think is dear to all of us, with the Milky Way. And with great pleasure, I welcome Laurent Eyer from the Observatoire de Genève. And he will tell us, I was about to say everything about Gaia, but this is so much, this is such a successful mission that this is completely impossible. So I think we will get some highlights about the multi-epoch, multi-instrument survey of Gaia. And before we get to that, let me introduce the speaker a bit further. I think we have known each other for, what is it, 20 years or something like that? So a long time. Also a long time ago, he got his PhD in 1998 from the University of Geneva. He then moved to Leuven, to the Catholic University of Leuven, where he spent his first postdoc for about 2 years. Then he went across the Atlantic to Princeton, where he spent another 2 years as postdoctoral fellow and had many discussions with the scientists there. And he came back to the University of Geneva in 2022 as a physicien spécialisé, working already at that time, and before that already, on astrometry, Hipparcos, and Gaia. And since 2009, he's maître de recherche, and so full professor at the observatory, and deeply involved in many aspects of the Gaia mission. So the people here who are also very much into Gaia, data analysis, construction of the solution, know you very well for many years. So please tell us about the latest news from the Gaia satellite. Welcome.
Thank you very much, Ralph. It is a pleasure to be invited here. Obviously, I will focus more on my kind of obsession. That's more on the variability of stars, but I will try to be a bit broad. So from the beginning, this is a slide that I've shown for a decade, but I modify it a bit. So the Gaia mission, in a nutshell, it's a multi-epoch, multi-instrument survey. It's a cornerstone mission of the European Space Agency. The observations are dedicated to all objects brighter than a certain limit. So the number of sources, it's more than 2 billion. It's doing multi-epoch measurement in astrometry, for the position, spectrophotometry and spectrophotometry, radial velocities, therefore a reduced number of sources, but which is above 100 million objects. It was launched in December 2013. It will end early 2025. And for the 10 years, the whole sky will be measured on average 140 times in each of the 9 CCDs and also in the BP, RP CCDs, which are giving these low resolution spectra, and 80 times in radial velocity spectrometer. The data is made available through public data release, and you can access this data in the Gaia archive. So globally, what is doing Gaia, so if there is a name, it's a census of sources, astrophysical sources, which are brighter than a certain limit. And if we look at the numbers, it's a mission of superlatives. So it's breaking many records in many, many places, technologically, also with the scientific results in the data processing. And soon, Champagne, if everything is going well, we will have 10 years of operation. It started the 25th of July 2014, so just a few months, and there will be 10 years of mission. So a bit, I'm also used to show this. Obviously, it might be a bit offensive for theoreticians. That's the Prof pyramid. And so what do you see? That's probably, I don't know if Uli, you know this astronomer, but probably he was a bit frustrated. That's my guess. And he was an astrometrist. And but deep, if you think, it's true what is. So at the really the base of astrophysics, you have astrometry. And when you have positions of objects, then you can do photometry and spectroscopy. So you have the spectroscopist and photometrist. And then you can start with measurements you can do modeling, stellar, interstellar matter, and you have a theorist. And obviously he had, these props had a little disdain for cosmologists. But I think it was just because often astrometry was a bit pushed down. And I think that's a fundamental mistake. So yes. So when you look at the importance of Gaia, now Gaia in astrometry, you don't have, for so many stars, you don't have anything better. In photometry, spectrophotometry, Gaia is doing a lot. You have also the spectroscopic instruments, which is deriving radial velocities in Gaia. That's also the numbers that are coming out of this RVS instrument is amazing. And there was a complement with the Gaia ESO survey to have a high resolution spectroscopy. So it's a bit amusing, but I think there is a deep truth in this diagram. So another way, when I present to students, I present this way. You have the three fundamental aspects in astrophysics. You have photometry, spectroscopy, and astrometry. Obviously, you have now gravitational waves, neutrinos from many years ago already, and cosmic rays also, which are older, that you can learn about the universe through these. But basically, you learn about the universe through photons. And when you have a single epoch, so just let us look at the astrometry, you can do 2D maps. And then when you have multi-epoch, you have parallax 3D map and proper motion. And what is interesting is also when you combine things. So when you combine photometry, spectroscopy, and astrometry, then you can do many, many things in astrophysics, like the standard candles, variable stars as tracers of population. You can probe the invisible with microlensing. You can do, well, that's a bit, you need a high resolution in photometry, but you can do asteroseismology. You can determine astrophysical parameters. So there you are really doing physics. And when you combine things. So I think there, multi-epoch is fundamental. And so just let us remind how Gaia is doing a census. I think there was a talk by Michael Perryman last year, so I won't go into much detail, but Gaia is rotating, has two fields of view separated by 106.5 degrees, and is scanning the sky continuously, 24 hours per day. And then the stars on the focal plane are just crossing. And if the star is brighter than, there is a sky mapper, if the star is brighter than a certain limit, then it is detected over all CCDs there, so little images, because when you look at the CCD, the camera, it's nearly 1 billion pixels. So that's the largest camera you have in space at launch. And I think it's still the case now. So 10 years later, maybe the military in US, but I don't know, but okay. So it's quite a record. Huh? On Earth, now you have that LSST camera is a 3 billion pixel. It's the record, but Gaia for 10 years was the record. And you see that to go from one CCD to the other, you have about 4.4 seconds. and to go through the whole field of view, you have 80 seconds. So obviously, from the L2 Lagrangian point, you cannot transfer 4.4 seconds, every 4.4 seconds, 1 billion pixels. So that's why you have these little post-stamp images. There is some processing on board, and then that transfer to Earth. And then you have the processing, which is which has to be done to calibrate all this. So why Gaia is really so amazing? So I hope I will convince you. But the first thing is it's an unprecedented astrometry for so many stars. And you have this very well-known diagram that was initially done by Eric Hugg and also by Michael Perryman. And you see that for me, that history is comforting because people are working. So here you have the different centuries, 17th century, etc. And we are here. We are here, okay? And you see that the accuracy of star positions through history, and you see that through centuries, people are improving. It's very comforting. People are working and they do better every century. But what you see at the end of 20th century, you see with Hipparcos and now with Gaia, a real change in the slope of this curve. In a few decades, we are doing what was done over several centuries. So we are really at an amazing period for astrometry. And I think there we are benefiting fully from the space, from the technology, from the computers. So everything is converging that it is making this possible. And the other point to see that with Hipparcos, there was only 120,000 stars. And here that's more than 2 billion. So the number of sources is just exploding. So what can you do with if you had with the data in astronomy? You have you can do a map like this very beautiful map, but you can also have 3D. So that's something that was done here. That was even something special for me that Stéphane Jordan did, and so you can explore the space. So globally, my point is that now science fiction movies, they should use Gaia for their interstellar travels. That's something they should do. But more seriously, what is quite amazing is that Gaia helps also for interplanetary travel. So there were data which were transferred for the New Horizon mission in order to be able to orient this spacecraft. And it helped also for stellar occultation measurements, for example, of asteroids. So obviously, these points are not they are not at all the main goals of Gaia, but through this, you can see already that Gaia, thanks to the astrometry there, is having impact where you could not really imagine, where, well, at least initially. You can also have proper motion. So if you have the constellation there, you don't have only the distance, but you have also motion. And so the stars are moving around. So that's also something important. But Gaia is also amazing for many other reasons. You have 3 instruments on board observing 24 hours per day. You have this astrometry, but photometry, spectrophotometry, and spectroscopy. You have multi-epoch, which are really simultaneous measurements. And this is something very strong, because when you see other projects like ZTF or LSST, which I find are fantastic projects, but the fact that the different bands are not observed at the same time or nearly at the same time is making the analysis of these data more complicated. It is really all sky, so Gaia is observing all sky. It's in space, so no atmosphere, nearly no bad weather except for the antenna on ground. And you have also stability. You have a dynamical range, which is enormous for Gaia. You have 21 in magnitude, so it's really enormous. Usually the telescopes, the mirrors are saturating. Here there is a system to observe bright objects as well. The number of measurements, we can speak, I think, about big data. In DR3, nearly 1 trillion CCD measurements for 34 months, so that's enormous. The selection function, because the scanning law of Gaia is very irregular. There was a bit change during 1 year of in the scanning law, but you can work out the selection function for the different sources you are interested in. So also that's a big difference from telescopes on ground. If you want to work a selection function, what is the performance of your instrument with respect to a certain phenomenon, then it's very difficult because you have cloud, you don't know the precision is changing, and so Gaia is also good. And also within the consortium, there is a cyclic improvement of the data, more data, better calibration, and also better artifact identification. So really that's with our work of the consortium to improve always. So here I didn't choose the astrometry. I apologize for my colleagues here. I thought I would show how in photometry things are improving from DR1. This is the mean, the uncertainty on the mean. So obviously more data you have, better determined is the mean, but you have DR1, okay, you see that that looks not that good. You have the features here, you have a bit vertical spikes distribution, you have these huge things, so you see that at magnitude 11, you are globally nearly as magnitude 19 or 20, so that's not that good. But in DR2, okay, that starts to be better, and DR3. So you see so there we see that there is not only the improvement of the number of measurements, which is going like the square root of the number of measurements, but really the calibrations are really improving. And we see that the precision on the mean is at below a tenth of the millimag. So it's a remarkable achievement. You have also another point is that you have the BP and RP low resolution spectra there. So you have about 60 samples. You have stars of different spectral type, and you see how they look. And so my surprise in DR3, in fact, I was a bit shocked when I saw this, is that you can extract sub-bands. So let us see what was done in Geneva Observatoire. I'm from Geneva. The specialty, the obsession was photometric calibrations. And here is probably after 25 years, 30 years of effort, what they achieved, my colleagues. So you have, so that's the HR diagram of the poor, because here you don't have parallax. You are just color versus color. And so you have the OB, AFG, KM stars, you have the dwarf, the giants, you have a problem a bit with interstellar reddening. And so with Gaia, with BP and RP, you can do such a diagram with extracting the bands. And this is the diagram you get. So again, I try to align the two. So this is amazing. So when I thought, I asked Michele Bellazzini, is it simulated or is it real data? I could not believe, because you really have the same structure. You see also the white dwarfs here. Yes, what we should say is that in SDSS, they turn it the other way around. And that's why I put but that's like we do in photometry. So really you have probably here, that's the halo. You have also the position of quasars. It's really amazing plot for me. And so in a way, you have this nearly for free. So that's kind of one of the, not little, but a byproduct of what Gaia is producing. Obviously, when you do then introduce the parallax, then you have the Hertzsprung-Russell diagram, you have the main sequence, the red giant branch, you have the red clump. Here it's elongated because of the interstellar extinction and reddening. And this is the color versus absolute magnitude. You have the white dwarf. You see this very amazing structure. Probably Michael Perryman talked about this, I'm quite sure. You have also there, for me, that was a bit surprising, the extreme horizontal branch stars. So really, the description of stars, thanks to Gaia, has been changed. There is no equivalent that has been produced. Now, if we look at the data release 3, that was the summary of ESA. You have 1.8 billion stars with different properties. You have the astrometry and photometry. You have astrophysical parameters. You have binary systems. And so we see that Heidelberg here plays a fundamental role in the astrometry, is the center of astrometry. And you have also a big participation in these object classification and astrophysical parameters. So we see that here in Germany, but that's not only in Heidelberg, you have other places where there is a very strong implication of Gaia. I would say also Gaia is attracting, you have a large implication of France, of Italy and UK. So all the big countries, they participate to this effort. And also Switzerland. So in Switzerland, what we do is concentrate on the variable stars. And that's, I will focus a bit more on this, but from a more general perspective. So that's the plan of the talk. I did the introduction. There will be a variability with Gaia, black hole detection, and Gaia citizen science. So we will go to some results. So here is the variability tree. When you try to have high level, what are the variable sources in the universe, the stars, but also the AGN or asteroids. This is a bit a summary that I did several years ago. So there also you see that Gaia, with this iteration of the processing, is improving every time. So in DR1, we were focused here on RR-Lyrae and Cepheid, type 2 Cepheid mostly. That's, we had a few thousand, 3,000 stars. Then for DR2, we had spotted stars, we had Myra long period variables, and then DR3, we start to cover nearly all types of variability. So there is this progression. We learn by doing, having first something relatively simple and improving. So globally, we are doing, I think, quite well in terms of describing globally the variability content of these 2 billion stars. And so here you have the different classes. You see that pulsation in the sample we analyzed is very large. Then you have rotation, and then we have eclipsing systems. And globally, we cover about 35 subtypes of variables. And we have 10.5 million variable source, 9.5 million variable stars, and 1 million AGN. So there, okay. So, and we have also, through another aspect, through false variability, we are able to detect 2.5 million galaxies. Here we broke a record. This is the largest set ever of published time series with a classification, and this, it's on the entire sky. So that's, it's making, it's quite amazing because you have many projects, Palomar Transit Factory, you have Ogle, the ZTF, you have many of these fantastic projects, but still we are breaking this record. So you can have also a global description of variability with a fraction of variable sources. And this is the color versus absolute magnitude. So you see that you have ZZ Ceti star, the white dwarf oscillating stars. You can see that you have the instability strip here with going up with the Cepheids, RR-Lyrae, and Delta Scuti. So you see also there with pre-main sequence stars that the further you are away from the main sequence, the more variable they are. So you have, I think that's the first time, again, that's kind of record where you can really have a complete description of the variability for many variability types. So what you can do is now to look at subgroups. And this is, for example, a case for pulsating stars, where you have here the clump of ZZ-Ceti. You have long period variables, you have Cepheids, RRL rays. And then you can start to compare this to people who are doing modeling, theoreticians. And so here is an example where you have the log TF versus the log L. And you have the prediction from a theoretician on the pulsating star, the beta Cephei stars. And you have also the delta Scuti instability strip. And so what we can say here, it's not working that well. So you have this region, the stars are there. So who is wrong or right? So that's a topic of which is interesting. Maybe what should be said is that these stars are rotating. Maybe rotation is playing a role. Changing the way that log TF and log L should be estimated, or maybe the models, they don't include rotation. And so that's maybe the models are wrong. So there is work there for the theoretician. What we see that there is a class of variables here that, okay, that's a long time they were discussed in the literature, but then we have a good sample of them. Then we have the delta Scuti, so things there seems very good. We could maybe improve a bit the border, but globally we see that for these pulsating stars, the models are quite efficient. And then you have also another puzzling group outside this instability strip. So that should be investigated. Another point here is that you can do, also I was amused by this, because with Gaia, you can do a HR diagram which is alive. Things are moving around. And that's also the first time you could do it. Some people were doing it with a Cepheid to show the loop because they have a loop. But with Gaia, you can do this. You can do this also for LPVs with a variable RP low resolution spectra, the RP. So here is oxygen-rich Myra. You have the loop. You see how much they vary. So that's in difference in color. It's 2 magnitudes. Here also, that's a very large amplitude. And you see how the spectrum with molecules, how they change, how it changes. And this allows us to determine if a star LPV is a carbon-rich and oxygen-rich. So, and we, in the DR3, we had 500,000 of carbon-rich long-period variables. You can do also various other things, so that just opening boxes, imagination from the light curve of RRL ray. What you can do is you can derive parameters, a Fourier series. It's very simple. You have the Fourier series, and you see that the metallicity is linked to some of the parameters. And now you can have the RRL ray stars. These type of stars, they have a half-a-day period. They have large amplitude. And here is the metallicity. And what you can see, okay, LMC has lower metallicity than the Milky Way. SMC has lower metallicity than SMC. You see also the Sagittarius here. You can describe, thanks to these variables and the shape of the light curve, the metallicity. It's quite amazing results. I would not have expected it at the beginning of Gaia. Furthermore, with these RRL ray and Cepheid, now in DR3, you have the largest sample ever published of stars with radial velocity time series already in DR3. So this is also, we break a record here. It's very good. You can use then to do a Bade-Wesseling method to derive the parameters of the star. Yes, you had also, in the focus product release, that we also produced the largest data set with radial velocity for LPVs. So really, we are in these records, in these superlatives. But also, this was huge variations. But also, in Gaia, you can do small things. So small is also beautiful. For example, the exoplanetary transit. So I like this slide because when I started Gaia, you have, obviously in Geneva, we are very strong in exoplanet. So there is one good astronomer, is good. He's not anymore in Geneva, but he's very good. He told me with Gaia, you will find 0 exoplanetary transit. So really, I was a bit upset with this. And so that my colleagues from Tel Aviv University, they worked very hard. And they produced a list of 214 candidates, exoplanets. 173 are known systems. So you see the transit. So that's from quite a lot of sources. And you have 41 are new systems. And in 2022, we confirmed 2 cases. These are the data. They are amazing. So you have the data. Here you have the transit. You have what was amusing is that they had TESS measurements, but they were not discovered by TESS. So we could compare the brown points are TESS measurement, and the black, red, and blue points are Gaia. I think it's quite amazing. So we have 2 exoplanetary transits. And also we have developed a collaboration with a NASA TESS mission, because everybody knows, I think, the TESS mission has a wide PSF. And so you can confuse the sources. And so with Gaia, we can say, oh, it's a background eclipsing binaries, which is mimicking an exoplanetary transit. And in 5% of the candidates, we can say, oh, that's bad. It's just an eclipsing binary, which is back. And in 5% of the cases, we can confirm the transit. So with Gaia, 5% of the case. And I'm quite curious now with cycle 4 for the DR4 data, when we will receive this, it will not be 10%. I'm sure it will more than double. It will be 50, 20%. It is to be noted that from the astrometry, there is Gaia 3b, an exoplanet, from the list from the astrometric exoplanet, which was detected. Also, I think there is some discussion about this one, but it's a true exoplanet. But maybe it was the astrometric solution had some problem. It should not have been selected. There is a complicated story, but now we have 3 exoplanets, 2 from transit and 1 from astrometry. Also, probing the low-level amplitude, we can see quite amazing results. This is, you have Kepler mission. Kepler is amazing mission, I think, because you have continuous measurements. It's very precise. And but then you can compare. So Gaia is not as good as Kepler in terms of photometric precision. And so you can look at the amplitude of Kepler for a certain number of stars and the amplitude of Gaia. And suddenly you remark that, okay, there is clearly a correlation to the level of few millimagnitudes. And when you look at estimates of the amplitude, you reach in the RP band 2 millimag with Gaia that are very probably significant. So it gives hopes that a few millimag amplitude in Gaia will be detected in DR4 and DR5. You have also in this same line, I was also quite shocked with this, multi-periodic behavior. So this is a star where you have the amazing Kepler data, and you have only 40 measurements of photometry of Gaia, 40 measurements. And what you see is that the 2 most significant frequencies of Gaia, they coincide with the Kepler data. It's quite amazing. So in a way, yes, here, a second. In a way, it's opening the door to have multi-periodic analysis in Gaia data, something I would have doubted many years ago. So really, the quality there is very good. Now I'm going to period luminosity relations. Gaia is very interesting, as I mentioned, when you merge things. You have astrometry and you have photometry, and you merge things, you have variability. And for example, we could show that the delta Scuti stars, pulsating stars, they have a period luminosity relation. So that's at the time we published this, that was the most complete. You can start now to discuss, is there a break in the law or is it non-linear? So it's putting constraints on the people who are modeling. You can use these standard candles with, for example, the Hartley rays. So you have streams in the Milky Way, and you can reach this point where you have Hartley rays. This is from DR2. And you have Magellanic Clouds, the center of the Milky Way, and you have holes there. That's because of the scanning law. We are less performant to detect Hartley rays. And there you can do the distance through the difference of magnitude. And there you see the Sagittarius stream. So I was amazed because globally that's known for several years, but globally with Gaia, you take the data, you see it maybe, let's say, be generous, 1 hour, and you find it so easily. I think this is amazing. People, to discover this, people spend a PhD. So maybe any student can find it very easily. And we see that these periodicity relations are very important. Here you have Cepheids. This is, I often say, that's a periluminosity relation with Hipparcos. You have the period that's in infrared photometry. And I remember that was Professor Mayer. My background is theoretical physics. So I was in the lecture of Professor Mayer, and he said, oh, there is a relation there. And for me, that was a cloud of points. So, okay, I was not very convinced. But then with Gaia, we see, okay, that's DR1, DR2, DR3. Okay, there is a relation. It's amazing. And so you can distinguish 2 sequences, that the fundamental mode pulsator, and that's the overtone. So really, you are able to calibrate, and that's where Gaia is very strong. It's not only astrometry, that's when you take astrometry and photometry and you merge them. And then you have this, I will do a little digression on the Hubble-Lemaitre law. Everybody knows this with the Hubble. And so there is a lot of discussion on this. And the way you calibrate, one of the way to calibrate is thanks to these Cepheids. And then you, from the astrometry, you calibrate Cepheid. Then you use Cepheid to calibrate supernova, which are in the same galaxy. And then you continue. So the graphical version, you have here the geometric distance. Then you have a modulus distance of Cepheid. Then you have galaxies which contains both Cepheids and supernova. And you have modulus of distance of Cepheid which have been calibrated like this. And then you have the supernova. And then you do this with the redshift. So that's how it is done. And you have the Hubble tension or the Hubble trouble. That's a very famous image where you see you have the derivation of the H0 from microwave background from far away in the past. And you have the direct distance. So there is maybe the tip of the red giant branch. But on my side, I published a paper recently. I have some doubts about this. So globally, there is a tension. So what is happening? That's Adam Rees, who got the Nobel Prize, is doing this study. And what we see now is that in the error budget that you see, the largest uncertainty is the supernova dispersion. And now the improvement is quite slow to find a galaxy which hosts supernova and Cepheid. And the largest uncertainty are Cepheids. And from EDR3, Gaia is the best option to calibrate the Cepheid. So globally, before Adam Rees was doing this with HST, but now he's saying very clearly Gaia is unbeatable. Just a more recent paper, there you see the issue of crowding, HST versus James Webb. So in red are James Webb, in gray are HST. And you see that the crowding, also there are many discussions now in the community, but I think there you see there is a very little effect of crowding. That's a comment on the side. However, Cepheids are still problematic. The Cepheids that you calibrate are very bright, maybe too bright. You have a saturation gating system in Gaia. You have color variations in the astrometric solution. That in the astrometric solution, you are using a mean color. So there is a discussion. And how to solve this? Okay, wait until the Gaia consortium and Heidelberg team improves the solution, or the astronomers, they are very, they like to find ways, or several Cepheids are in clusters. And so you can determine the distance of the cluster with Gaia. They are not that bright. You have stars which are normal. You have a range of colors, so you avoid some possible biases. And globally, what is happening is that one cluster Cepheid counts like 9 Cepheids. You discover one Cepheid in a cluster, and then you have 9. It's like 9 to have 9 additional Cepheids. And you see that Adam Rees did use this, and you see that you improve 5 to 7% the uncertainty using this technique. So it's very interesting that you are using these stars of a cluster which hosts a Cepheid, and you are able to circumvent this problem. And the problem there is that with these results, it's even enhancing the Hubble tension. I will maybe a bit speed up there. So let me see. Yes, maybe what is important here, the perspective with Gaia is very good, because the random errors, they are going like the square root of the mission length, position and parallax is the same, and the proper motion, it's even stronger because you have the baseline. And so from the 34 months to 10 years, you improve all the solution by nearly a factor 2. And this is without counting the improvement, the global improvement in the data reduction. So globally, these coming years, still there will be major improvements to these estimation of calibration of standard candles and all topics in Gaia. Okay, so maybe I will skip the black hole. So maybe everybody heard the black hole. Maybe the important point is that with Gaia, every instrument is capable to detect black hole. And so now we have astrometric binary that was detected this black hole 3 of 33 mass, but you have also ellipsoidal variation. They provide candidates through the photometric variation that you can have candidates for black hole. Obviously, spectroscopic binaries, you have also candidates of black holes. And this is, so every aspect of Gaia. So Gaia is a black hole detection machine. That's exactly the point there. You can also detect black holes through microlensing. So there was a kind of proof of concept where you have a microlensing event, and normally you have a degeneracy if you have only the photometry. But when you have photometry and astrometry, then you can lift degeneracies and you can determine the lens mass. So we hope that in DR4 we are able to merge the astrometry and photometry, and that would be very interesting. For now, there is only one black hole which is detected. That's with HST with this method. Okay, I will go. Unfortunately, there are many other topics. Many you can. I gave a talk. I made maybe 10 more slides saying, okay, you can speak at this, at this, at this. It's enormous. What I will say is that there is a citizen science project. That's the first citizen science project we did on variables. So typically here you have a Cepheid with a 4-day period. You have a beautiful light curve. You have the color variation. So Cepheid, when it's pulsating, it's getting brighter when it's bluer, right? And you have also the position in the Milky Way. So there, the people, they look at these stars and they classify them. And we have 2 campaigns, and we have 220,000 classifications. So people clicked. You have people who are amazing. So I'm very impressed. We did also the first page of the most read tabloid in Switzerland. We see that the character here, that people stealing bags in the trains, they are bigger characters. But on surface, we were very good. Counting the stars, and we are beating Joe Biden, who wants to be president for the next election, candidate for the next election. So I think there we were very, we had quite a good impact. And but it has really an impact. We think that we learn things by doing this project. We did several discoveries, interesting, very special white dwarf, newer coronae borealis that are not in the list of publications we have already. So really, the citizen science, they bring something. And also, we will use this effort to improve the core. So really, I was very happy that this citizen science project is functioning. Conclusion. Maybe 3 minutes, okay. Conclusion, when you look at, so that's quite, people in Gaia, in the consortium, they are too humble. That's my impression. I was at EAS meeting, and that's there I discovered this diagram, which is, for us, working so many years in Gaia, is very comforting. So this is from ESA. You have all the years. You have the publications for all the mission. Okay, you have Planck, Herschel. Well, you have all these missions. And then you see Gaia is going. You see that nearly you double, not far from doubling, all the number of publications from all other missions. So that means Gaia data is extremely used, and this diagram is a real success. This is for just the ESA mission. If you look at citations, you can do also for DR3 and EDR3, etc. But if you look in all astronomical literature, I was baffled by it. In 2018, for DR2, now you have several years, so it's good statistics, you have 68,000 articles were published in astronomy. So that's quite a lot. Astronomers, they like to publish, apparently. And I let you guess which article was the most cited. This is the Gaia DR2 summary of Anthony Brown. It's so among you take gravitational waves, you take white dwarf science, whatever, that's the most cited paper with a 7,000 citation. So I think it's really, that's demonstrating by number, by some statistics, the impact of Gaia. And then there is an international recognition. There is a German Astronomical Society Award, which was given to Erik Hug, Perryman, and Lindegren. There is a Shaw Prize, which was given to Lennart and Michael Perryman. And then there is also the Berkeley Prize, which was given to the Gaia Consortium. So it's working so many years, and when you are in the little details, it is a bit sometimes heavy. You confront problems, you try to solve them, but then we see the impact and also the international recognition. It's a very good feeling. So I hope that I presented this mission, and but obviously to present globally, I selected topics that are a bit my favorite topics, but to present this mission with so many results, it's a daunting task. I also hope that I convinced you that Gaia is really amazing mission. It has an impact on variable source, instability region, distance scale, discovery of black holes. That's the topic I touched slightly. And also all these aspects are touching time domain astronomy. So astrometry with parallax and proper motion, you have multi-epoch. So multi-epoch is fundamentally rooted in Gaia. And also what I would like to say is that Gaia is a human, technical, and scientific adventure. That's for me the most, most important thing. It's a real modern adventure. Obviously, we don't risk our lives going on a little boat crossing the Atlantic, but it's a real adventure. So thank you very much for your attention.
Thanks, Laurent, for this fantastic and very emotional and invested overview of what Gaia has done to all of us who are astronomers, astrophysicists, theorists, and observers, and of course to the many groups who work on that. Many thanks. The podium is open for questions. Who would like to start? Yes.
Okay. Based on the apparent Hubble tension, is it possible that somehow the real Hubble parameter is higher in a local universe and lower at high redshift?
Yes, so we see that I would say that the work of Adam Rees is quite amazing. I don't know him well, but I know him a bit. It's quite amazing because he had initially like a smoking gun of that of this difference. And the more he works, the more this tension is getting strong. And I think there is really this tension is real. So I think I don't see how we can escape it now. So that's the more I follow this. Yeah, so I think there is a real problem. And so I don't see how to solve this, for example, with this tip of the red giant branch. So there also, thanks to variability, we were able to understand a bit the tip of the red giant branch, and we could see that the people who are doing this calibration, they mix up a bit different things. We were able to, I mentioned this, that to reverse engineer what they are doing, and we see it's not that good. So I think there, all these method of a local universe is converging, is quite coherent in a way. So I don't see how things could be changed, but maybe there is something that we miss. That's all of it. But I think from so many sides, it's difficult to reconciliate that.
Next question, Joachim Wamskans.
Well, great talk, great mission. Thanks a lot. I have two questions. The first one is, can you display the Hubble, the Hertzsprung-Russell diagram alive again? I find this so amazing. And just run it in the background.
Yes. Oh, I had many slides. No, I missed it. Okay, yes. Yes, this one.
Yeah, okay, great. And my question is, can you say a little bit about the quasar variability? You said 1 million quasars were detected as variable. What are the main results from the analysis there?
So there, with these quasars, what was quite amusing in the paper of Maribel Carnerero, she showed that we were able to determine for one object a time delay. So that you have the two images, and we were able with Gaia to, which is known, but suddenly we were not thinking that it would be. That's one of these results where we were thinking, when they spoke about this, I said, we can't do it. But in one, at least we have a demonstration that it's working. And so we didn't, we study the structure function, we determine the parameter of the structure function, but that's global description of the variability of quasar. That's globally what I would say. I don't remember any strong oddities or things like this. I think that's quite standard. Yes. So if you look at the, so we see that we can improve. Here, that's from the machine learning. You don't have the square shape in astronomy. So that you have a corner here. I think that the machine learning, we use the random forest and with a training set, and he's doing a bit weird. So we hope we improve this in the DR in DR4, but it's still amazing, I think.
Further questions?
Yes.
Yes. You should sit further down. Fabian Schneider.
So thank you very much for this talk. Since you had to skip the black hole part, can I ask what the prospects of that are?
Yes, but that in fact, the black hole as it was found was from a very special sample. And I think we can't really, we are not today in position to say how many black holes Gaia will discover, but we can imagine that, because I said the selection function in principle, precision of instrument, the selection function can be determined, that it wouldn't be too difficult to have an estimate of these, of the capability of Gaia. And I guess that there will be many black holes which will be detected. I have no doubts there. Yes, and yes. Yeah. Yes. Yeah, yes, but you have a, yeah. Yes. But we are already, yes.
At the moment, you cannot do such. At the moment, you cannot reasonably do such a calculation because you have no idea about the underlying population. I mean, you have an idea, of course, from stellar population synthesis, but the more interesting question is to use the detections to get information about the population rather than the other way around.
Yes. Yes. So in fact, yes. So what happened is that following the presentation, so in Geneva we kept it secret, so obviously to our non-Gaia colleague, and we have a team in Geneva who is looking at models of the formation of black holes. And so they immediately after they asked Barry, okay, if I give you a population, can you tell us how many Gaia would detect? And I think Barry Hall will do this, knowing the general properties of Gaia, and there will be an estimate. And then what will be interesting that when we have the data, are these objects in? So that will be very interesting, yes. So no, so that's totally possible, and I think it's not that difficult to do estimations. So the point here, as I said, this object was detected with a very specific sample, with a very, so we were looking at some extreme solutions, so it should not be, it is, I'm certain, it's not the only one, there are many.
So next
Uli?
question, Uli. Bastian.
Not a question, a remark. Half an hour ago, you said the Gaia people are too modest. Now you are too modest. I mean, what I really think it will be a 3-digit number.
Okay. Okay.
So maybe I intersect a question. So I'm wondering about the future of Gaia, right? Now it's almost 10 years that it is fully operational. Can you go another 10 years or 20 years or what is?
No. So there could be always technical problems with the mission, but the limit is the cold gas, because you need to have cold gas to sustain the way Gaia is rotating. And then this is coming to an end early 2025. So we know that there is a hard limit. We have no way to extend it. And so now there are discussions how to use the last months. Will it be an operation or maybe doing a certain number of tests? But globally, these 10 years, that won't go further. So that will be, okay, initially it was planned for 5 years. So we should be extremely happy.
But can you do a hot mission like with Kepler or something?
No, I don't think so, because you have the TDI, well, maybe you have the TDI mode, the synchronization should be, it's quite complicated.
Really?
I would say no, you can't do.
It's quite simple. It's analogous to the cooling agent for the infrared missions. If it's done, it's done. And in the case of Gaia, it is the steering gas, cold nitrogen gas tank, used to control the rotational motion of Gaia that will be empty around Christmas this year, few weeks after Christmas. And as Laurent said, we are planning to do some technical tests to understand a few things in Gaia and also to help other missions in the future. We will be spending the last 4 or 6 or so weeks of gas available, not for scientific missions, because we already have twice that we got, but that we had promised, but to do some tests. So probably the end of the mission will be immediately before Christmas, and the next few weeks will be these tests, and then Gaia will be disposed of.
Okay, thank you. So let me check whether we have questions online. I see nothing, right? Just punch in if you have, maybe you can check.
No questions from the student of Saskia? No.
Oh, you put pressure on them. Speak now or be silent forever. Yes, very good.
So there were many possible improvements for. Okay. So there will be more improvement for data release 4 and 5. And what do you think is the most important part of?
Oh, that's difficult to say, yes, but there will be improvements. I think the astrometry, the 0 point of the astrometric solution, the photometric reduction will be improved. So the calibration, not playing on the number of measurements simply. So then we see that some problems are identified, and then you improve things. Now to see exactly where it will have a very strong impact, it's very difficult. What I would say, for example, for the people who are studying variable objects, you will have a 10-year baseline. That means that, yes, the frequency resolution for an object that you suppose periodic, if it's strictly periodic, then the frequency will be very tightly defined. And I think that's something that's Connie Arts who showed me. I said, this will be fantastic. And so there is possibility with these multi-periodic studies also that to start to have several periods in Gaia data with very high resolution. It's fantastic possibility. There are instrumental effects also that is polluting. That's another problem. But globally, we see that there is a potential that was never envisioned. So, but you have many improvements.
So the future is bright.
Oh yes, for these coming years. Oh yes, coming years they are fantastic. And also in the classification using machine learning techniques, we see we have new ideas. The domain of machine learning is kind of exploding. And so we are changing methods. And also what is good, I have to say, with this iterative processing is that we have now we have the DR3 baseline. And so now when somebody is coming with a new idea, okay, so how is it performing with DR3? And we see if we can improve or not. Do we understand the improvement or not? And so at the beginning of the mission, that was a bit difficult because you have many different methods, typically in machine learning, saying, oh, no, but you should use this and that. And we were trying, and we were a bit in the kind of fog. It was, okay, but now we have a good understanding of the sample. And so we have this progression that is possible. And I think that's a big advantage we have now, to have this iterative way to work.
Very good. I think that is a good starting point or ending point or prospect forward to end this talk. Before we thank Laurent for this fantastic overview, let me do 2 announcements. First is next week we will have Mario Flock from the Max Planck Institute for Astronomy talking about exoplanets. Stay tuned, more information will come as the week continues. There will be dinner with the speaker at, as I understand, you are organizing it, at Hemingway's, right? Will there be drinks before?
Okay, so we have a table booked at 6. If we arrive, well, we can have drinks before, of course. Then it all depends on how many we are who wants to stay for dinner, but there's no problem in having drinks before, and we can.
All right. With that, was a great talk. Thanks for.
Thank you.